Hi everybody, Mrs. Pesic here,
And Miss Bella here.
and we are looking at section 6.2, comparing functions. The objectives today are to compare the properties of two functions and to estimate and compare rates of change.
Okay, in this lesson, we're going to compare the graphs of linear, quadratic, and exponential functions. So our first example, we're going to compare the average rates of change of two functions. So we have George, and he tracked the cost of gas from two separate gas stations. The table on the left is going to show the cost of gas for one of the stations, and the graph that will be on the right is going to show the cost of gas for the second station. So what we want to do, if we have information in two different setups here, we want to compare the average rate of change and explain what the difference in the rate of change represents. So just a little helpful hint here. To find the average rate of change over a data set, you're going to find the slope between the first and last data point. Now, if we want to remember how to find slope, we take maybe just a little refresher here, also on slope before we do this. Your slope is usually m, so we say y2 minus y1 over x2 minus x1, just if we don't remember how to find that slope.
Okay, and it is just interesting to point out that the information for gas station A was arranged in a table, whereas the information for gas station B was organized in a graph format. But we still want to find the slope for the first and last data points. So to speed this up here a little bit, if we do this for the gas station A, we would take our difference in our y's from the largest y to the smallest y here, the last data set minus the first data set, over the corresponding x values. So we get this equation, and it turns out to be approximately 3.0. And then when we do this for the second data set, we have to kind of figure out what these ordered pairs are. If we use this ordered pair right here as 0.5 comma $2.31, and this one up here as being, what did I use, 13 comma 38.15, then when we find the slope of that, we get 38.15 minus 2.31 over 13 minus 0.5, and that turns out to be approximately 2.9. You can check this with your calculator.
So what do these numbers mean? Well, our average rate of change for gas station A was about 3.0, and the rate of change for gas station B was about 2.9. Now, in this situation, the rate of change is the cost per gallon for each of the stations. So our conclusion can be that the cost is less at gas station B, because again, it was at 2.9 per gallon, whereas gas station A was 3.0. Okay, our second example here, and this one you're going to need your calculator, so why don't you make sure you have that ready and powered on for us. We're going to sketch graphs given that we have some key features here. So the graph for the height of a diving bird above the water level, h of t, and feet after t seconds passes through the following 3 points, 0, 5, 3, -1, and 5, 15. So our goal is to sketch a graph of the quadratic function that models the situation, and find the point that represents the minimum height of the bird. So what's the lowest the bird would go. Now, we're kind of giving you a setup for the equation. We are going to use the function h of t equals at squared plus bt plus c. So just our basic quadratic. And we're going to use those 3 points given. I'm going to plug in for h and t in each of them. So our first point is 0, 5. You notice in this case we're going to plug in anywhere we see a t, we'll put 0. So we have 0 squared and b times 0. Wherever we see an h of t, we will plug in 5. And just reducing that, 0 times anything is 0. So I have 5 is equal to c. My second point, 3, -1. Again, I'll put in 3 wherever I saw a t in the equation. So we have 3 squared here and a 3 times b at that point. -1 for h of t. Clean it up a little bit. You have -1 equals 9a plus 3b plus c. Our final point, 5, 15. Again, once more, 5 in for the t's. So at this point and that point, 15 in for h of t, and clean up what we have for 15 equals 25a plus 5b plus c. Now we're going to need to solve that equation, and we're going to solve that equation by using inverse matrices.
Okay, so to solve this system of equations, we're going to use inverse matrices. Remember that we want to have a coefficient matrix times a variable matrix, equals a constant matrix. And we learned about how to solve systems back in August. So what are the coefficients on these? For this first one, I don't see any A, so I could think of that as 0A plus 0B plus 1C, and that's what's equal to 5. So my coefficients here are 0, 0, and 1. So I'm going to fill those in here as my first row of the coefficient matrix. Next row is going to have 9, 3, and a 1. And the last one's going to have 25, 5, and 1. Notice that the first column here are really the coefficients on the A, the second column are the coefficients on the B, and the third column are the coefficients on the C. What are our variables? Our variables are A, B, and C, and the constants are 5, -1, and 15.
Okay, now when we were solving inverse matrices, we're going to use our Inspire to help do this. Another way we thought about this was really, we called our coefficient matrix matrix A, our variable matrix was X, and our constant matrix was B. So in order to solve for that matrix X, we solved this by saying X was equal to A inverse multiplied by B. So this is when we're going to need our calculator to key that in and solve it for us. One more over all the way at the end. There we go. Okay. All right, so on a calculator page, we're going to go to menu. Well, I guess we can go to menu. Yeah, or we can go to the little next to the book. That's probably easier. Next to the book button. Right there, this one. Technical difficulties. Okay, right here. That one. Yes, that one. Okay. All right, go to our matrix setup. We have, that's a piecewise. Nope, that's not it. That's piecewise. Down. There we go. Okay. So that's the one that lets you choose. So 3 rows, 3 columns. That is correct for our first one. So to set this up, we're going to have 0, 0, 1. Then 9, 3, 1, I believe. And then 25, 5, 1. So that was matrix A. We need to take A inverse. So we'll now raise that using the caret key to the -1 power. And now we're going to arrow down, multiplied by, go back to the button next to the book, choose that 3 by 3 again, but this time we're going to say it has 3 rows and 1 column, and fill in what matrix B was, which we might need to look back because I don't remember what those were. So 5, -1, 15. All right, so we have it keyed in. We'll hit enter, and it tells us we have our matrix of 2, -8, 5. All right, so that tells us that in this case, that matrix A, B, C was equal to 2, -8, 5. So that means A is 2, B is -8, C is 5. So if my original equation here, again, was AT squared plus BT plus C, we're just going to fill in that information. So we'll put in the 2 for A, -8 for B, 5 for C. So this here will be our final equation that we got from solving the inverse matrices. Now we were also asked to graph that. So here is the graph of what that function would look like. And we want to find the minimum height of the function. So the minimum height will always be at the vertex. In this case, my vertex, that lowest point, is going to occur right here, which is at the ordered pair 2, -3. So my minimum height is going to be the y value 3 feet below water level in this case, since we have an application.
So you could type in that function into your calculator to find this. This is one that we got right here, 2t squared, but remember use x's. So 2x squared minus 8x plus 5 on a graphs page. And then when you do that, you will see this graph, and you could even use analyze minimum to find the vertex. And then you can see that this diving bird actually ends up 3 feet below the water level. All right, so let's talk about comparing exponential and polynomial functions. So if we want to compare the end behavior of the functions f of x equaling -x squared, you know that's just been reflected over the x-axis. Can you fill in the blanks here? F of x approaches what as x approaches -infinity? Remember, as x approaches -infinity means as we go to the left, what's happening to the function? Well, it's dropping down to -infinity, so we fill that in here. And as x approaches positive infinity means as we go to the right. So as we go to the right here, what's happening to the function? It's also dropping down to negative infinity. So that's how we can analyze the end behavior for the first function.
Okay, for our second function, we're going to do the same idea. Let's keep the same colors here. So the first part, f of x approaches where as x approaches negative infinity. So we're looking to the left here. And again, we'll put that in here, left. Again, what's your y value doing? It is going down. So this would be a negative infinity. And if we look to positive infinity as I'm going to the right, what is my graph doing? So f of x, again, it's slowly growing, but it is growing up. So this would be a positive infinity. All right, and I think that ends our videos notes for 6.2. So thank you for watching. Be sure to take notes and bring them to class with you.